Okay, today we'll continue our course devoted to public health informatics and technology. And today we'll cover a very important topic, which is data quality. Because in public health, it's very, very important to work with a high level of data quality, because we have data from different sources that come with different formats. And we need to be sure that we have good data quality to feed this data into different algorithms and to get accurate results. Now, so today I will just show you how we work in public health with data quality. We try to improve data quality, and how we work with data. It's also, we call it data pre-processing. So we pre-process the data prior to feed the data into various algorithms, prior to get some results that are valuable. Okay. Now, I just would like to share my screen, and I will show you a few slides. Okay, so today we'll talk about this data quality. What I would like to say that we will discuss today 5 steps in data pre-processing before various algorithms, including machine learning, for example, because machine learning now is one of the most efficient algorithms to extract the different patterns, different information from data, and even forecast of what would happen, let's say, in some future. So that is quite important thing. And the first step, we transform the data to different. It's not necessary to pandas. It's written here pandas because what we do. It is a very efficient tool, very efficient data standard now, pandas. Pandas is rich of different algorithms that speeds up the processing. So that is quite important, speed up calculations. So we do transform to pandas data frame. That is quite what we do. Second of all, we remove outliers. Outliers, very nasty thing, because outliers, when you do not remove them and use machine learning, you have a chance that machine learning will be trained on outliers and will ignore other data. So this is not what we want. So what we want is to remove outliers. We want to remove outliers. And now we have data cleaning. Data cleaning is not only to remove blanks. So remove that the entries that have some features, and we'll talk about this. And finally, we have z-scoring. It is number 4. We'll talk about it, and feature engineering. So we will cover these topics. So first of all, I would like to refresh your memory. And we covered descriptive statistics. In descriptive statistics, what we have to is to go and calculate, for example, mean, median, quartiles, variance, and standard deviation. In inferential statistics, it's a very, very important tool in public health informatics, because we create some knowledge about the whole population that can, for example, include, I don't know, 100,000, millions of people, but using just samples. And this is a whole paradigm that we already covered this in general terms, and we will come back when we will talk about the data, how data store, and we'll do this next time. So inferential statistics is the way we take samples and we recover from samples knowledge about the whole population. This is called inferential statistics. I just would like to refresh your memory about quartiles. Okay, so this is from last lecture, and I just would like to once more refresh your memory about that. The thing is that when we have a data set, for example, 3, 4, 4, 4, 7, 10, 11, 12, 14, 16, 17, 18, we at the beginning need to put them in order because original data set was here, 4, 17, 7, and so forth. It's a very, very simple program in Python. They can do it. It's very, very simple. All right, so with that we have that ordered data set. And what we do, we identify, now step number one, the second quartile. The second quartile, it cuts the data set into equal parts. The first one has 3, 4, 4, 4, 7, 10. It is 6 numbers here, 6 elements. And we have here also 6 elements here, 12, 11, 14, 16, 17, 18. It cuts in 2 equal parts. We call it partition because it comes right in between of 2 numbers. And because it is even number data set, even number data set. But if it is odd number, of course, this number will be right here. It will be a real number, not partition. But here we have partition. It's in between. So what we do, we take 10 plus 11 and divide it by 2. Okay, and then we have 10 and a half. And this is, we call quartile Q2. Okay, same thing we do here to the left. It is partition also. It is Q1. And here is in between Q3. So we have here the first area. It is Q1 area. It is from the smallest number to Q1. Okay, and we have 3, 4, 4, 3 numbers here. Then we have Q1, Q2, and Q2, Q3. So we just don't care much about this Q1, Q2. We would like to see the whole area between Q3 and Q1. And this one is called IQR, interquartile range. As you remember, IQR. So this number is 4, 7, 10, 11, 12, 14. And this is a very desirable area because these numbers are least vulnerable for different outliers. So outliers can be here, can be below, here, it can be above, but it is very unlikely that outliers in the IQR area. It is 50% of the total data set. For example, we have here is in this data set, we have 4, 7, 10, 11, 12, 14, 6 numbers. And here we have 25% below Q1, this boundary. And we have at the high edge, we have also 3 numbers. It is also 25%. And IQR has 6, so it is 50%, 50% IQR. And IQR range, by calculation, it is Q3 minus Q1. So within this range, we have 50% of the whole data set. So it is Q3 minus Q1, okay? And this one, it is IQR, which is 11 in this case, yeah? 11 in this case, 15 minus 4, it is 11. So IQR is 11. Okay, so what we do next, we take the box plot, because box plot is very good to visualize the data set. And we have 10.5, this is our median. This one between Q3 and Q1, we have IQR. IQR. And IQR, in our case, has 6 numbers, as you remember. We have numbers in this area between the smallest number and Q1. It is 3 numbers, and here is also 3 numbers. So we have 50% in this non-shadowed area in this window. Now, what happens is that there is no mathematical proof of that. It is just empirical. So in data science, we use the following rule to eliminate outliers. And this rule shows the following. So we call this is IQR, and this is whisker high and whisker low. Okay, so what we have here, we would like to build now 2 inequalities. The first inequality is the following: Q3 plus 1.5 IQR. Okay, so you take IQR, multiply by 1.5, and plus Q3. So you can be somewhere here. So if you have data that are above this number, these are high outliers, and we will eliminate this data that are higher than Q3 plus 1.5 times IQR. Second inequality, it is Q1 minus 1.5 IQR. And that one is data, here, data, less than this number. We call this low outliers. So they are placed somewhere here, and we cut them too. Okay, so that one, that is criteria that we use usually when we would like to eliminate outliers. Now, what we have here, we have, for example, a data set where is the lowest number is 4. And what we do, we just draw a box plot, and we have this plot here showing that Q equals 4 is right here. And it looks like it is outlier. It is when you calculate 1.5 IQR times IQR plus Q3. Okay, this is Q3. You will have this data inside, but if you do Q1 minus 1.5 IQR, you will see that 4 is below this limit, and we need to remove it. This is an outlier. Okay, so what happens here? We removed this 4, and I have this data set. So the data below. So the whole data set is here. And you see what happens here. This is very interesting. The whole cluster of data are here. And this looks like also outlier. And there is an argument what it is. It is outlier or not. So 20 is within the limit, within this Q1 minus 1.5 IQR. So it's not less than that. So this is not an outlier. But some people are a little bit suspicious that it's maybe also an outlier. I will just show you a method, very simple, that you can use if you have some suspicious data point. It is outlier or not. It is double check method. Very simple. Maybe you don't find it in literature, but we use it in data science for people who are working in public health. We have some, after cleaning, we have outliers. We still have some numbers which are suspicious a little bit for that. All right, so let us just, I will show you one thing. It is a very interesting thing, a very interesting method. Very, very simple. That will show you about number 20, which is also suspicious for outlier. So 4 we eliminated. It was 4 eliminated. It was outlier. 20 is question mark. 20 is question mark. And what we do now, we calculate, this is a Python code that calculates the ratio mean and median. Median. Okay, so you calculate this ratio using this very, very simple Python code. Okay, and we calculate it, and the output is 0.96. This is the result. All right, so we go now next. We eliminate 20. All right, to take it out, and again calculate the ratio without 20. And you can see that actually the without 20 or with 20, it doesn't change. It is 0.96. So 20 is not an outlier. 20 is not an outlier. 20 is a legitimate data point in the data set. So what you do, as I said, you calculate, if you suspect some outliers, you have to calculate the ratio between mean and median, with and without, and see what the change was. I will just illustrate you on this example. So you take a data set, and this data set, it is negative 200, which is, of course, we suspect this is an outlier because it is, here is 52, 57, here is negative 200. So this is an outlier. And also 38, we may have this an outlier. Okay, so instead of going and to plot the box plot, we calculate the ratio mean over median using this very simple Python code. And with, we have negative 200. The output is 0.67, so 0.67. And without, it is 0.95. It is a big jump. So it is 67% and 95%. So it is absolutely evident that this is an outlier and it has to be eliminated. But what about 38? So it gives you output 0.95 and something, almost 96 with and without 0.96. So it is just difference very, very tiny. Okay, so that is not an outlier. So 38 looks suspicious, but it's not an outlier. Is not an outlier. That is the way we also check some suspicious number. So I will just to recap. So we have this formula for outliers, greater and less. This is Q3. I already showed you plus 1.5 IQR. This is Q1 minus 1.5 IQR. In both cases, if the data greater or less than this number, Q1, this you eliminate, okay? But suspicious, you do this one. And just to calculate the difference, it is, if it is big one like here, you have to consider this as an outlier. If it's not big at all, like in this case, okay, so that it is not an outlier. It can have valuable information, regardless where it's located. Now, what we do next, I would like to show you a data set. So we have name, Mary, Peter, John, Larry, Dan, Nancy, and Paul. And here we have H1, H2, H3. They are some features. Okay, so for example, you study some labs, and here is an income, for example, for people who get $1,230 a week, then it is 700. So you just put in this table, right? And here is some lab tests. So you would like to find out to use, for example, some algorithm to see if there is some correlation, what's going on, how you to process. Maybe you will add some features, maybe you subtract some features. Okay, so you need to work with this data. And when I show this to my students, some of them say, "Oh gosh, they was wonderful data set. Look at that. There is no blanks. There are no some weird characters in here. So everything looks very good. We can use now different, for example, algorithm without any thinking. But actually, this is a bad data. Bad data. So it looks like very good from the first glance. However, in fact, the data very, very bad. And we need to take care of this data. What do you think why it is bad data? Because first we will move this Excel file into Pandas data frame, not this Pandas data frame. That is how it's called, or some people just call it Pandas DF, and some people just call it Panda. Actually, it is Pandas DF. DF, it is data frame. You see, data frame, Pandas. Okay. Now, what happens is that first we need to import Pandas SPD. Okay, and when you did it, you can read Excel file, because this was an Excel file. You can put it in here, and this is a path to this file in my computer. So this is my hard drive, and this is the path to my computer to pass this file. You know how to do it. You just click with your right mouse on the data, and it gives you a path. You copy this path and put it here. It's very, very simple. So, and this is DF, gives you print of the data set already in this format, new format, which is Pandas data frame. If you put here parentheses, open parentheses, close, it gives you just a few lines. Okay. All right, so when I did it, I have that one. Okay, so that is what it is already Pandas. Pandas DF. Pandas DF data frame. You have numbers. And this is without any change. You have Mary, Peter, John, and so forth. This is H1, H2, H3. These are features. So people sometimes say, oh, so why we need to bother to go to Pandas DF if Excel is perfectly okay? So what happens here? We can examine now the box plot. Box plot, it's very, very good, but can be presented in terms of when you deal with Pandas DF. It's very, very simple, just one column here. So you just import your plotting library of Pandas, and you just put columns that you would like to plot. It is H1, H2, H3. You don't need to put name here, because name is just, you don't need to worry about the names. Okay, and then you have a box plot, and then you have terrible thing happens. It's terrible thing. You see what happens here is this one. So this one is big H3, it is big data, and here looks like 0. So many algorithms we have in public health informatics, including machine learning, they will ignore this data. They will ignore this data too. They will ignore the whole H1. They ignore H2, and they will work only with H3. And if H3 it is income, so they will just give you some, I don't know, some information about income, maybe just some kind of graph or something, but they will ignore this column and this column. So this is no good. And therefore, I wrote that this data set is bad for further analysis. What we do, we use the so-called standardization or z-scoring. Z-scoring is to put any value, for example, for Mary or for John here, and also different columns, H1, H2, H3, you put here, minus mean divided by standard deviation for each column. So you do for column H1, H1, H2, H3, and you calculate now data. However, you calculate now in terms of standard deviation, and you know that from negative standard deviation plus to positive 1 deviation, you have 64% of data. Then you have a 95 and 99. So Z would not be typically not be between -3 and +3, because now we calculate values in terms of the standard deviation. So they will be localized here. So you won't see any more thousands or 10,000 or millions. You will have from -3 to +3. Let's do this. And we have also normalization. Normalization, it is between, you put data from 0 to 1. Okay, this is called normalization. We can also do, but we don't use it so often. We use standardization. So in normalization, your Z values, but it is a little bit different, as Zn will be greater than 0 and less or equal 1. So this is called normalization, but we don't use much normalization, but sometimes we use it. And in standardization, when you do this algorithm, which is very simple, in also data frame, because we use here data frame. You see df, it is data frame, and you see that we have a file, that one. So the maximum, it is 2.4, as you see, 2.43. As I said, will be between 3 and -3. And now you don't have thousands anymore. And the data of the same order. And this is wonderful. So this data clean and very, very good. So we transferred bad data into good quality data. We did only one thing. It is standardization using z-scoring. Z-scoring. So that is quite important. And I will just put you here. The process is called z-scoring. Okay. Now, what I would like to show you is this one. So suppose I have now data set where we have blanks. So this is a blank, this is a blank, and this is a blank. All right, so we have 3 blanks. Sometimes we have very weird characters. For example, sometimes you can see here some, I don't know, some $sign, for example. Here can be some percentage. So some weird character that means nothing. It is very, very common because, as I said, that in public health, we have data coming from different sources. And when you do integration, and I will also teach you how to do integration, if you do integration in the wrong way, your data will be full, will be infested with different unwanted characters, and how to eliminate all these characters. Okay, so it's very simple when you do the pandas data frame transfer. When you take your data from CVS, comma separated value, CSV, or you have Excel file, okay, and then at XLS, anything, here, there's many different. When you transfer this into pandas data frame, okay, then things are much facilitated because we have a library very rich in pandas data frame. So you have here 1, 2, and 3. So what you do, suppose you have also some kind of maybe some weird characters, okay? So what pandas is doing? Pandas data frame, when you go to pandas data frame, it makes all unnecessary, all blanks, all kind of weird characters. They just mark them as NaN. It is very common in data analytics. So this is an abbreviation of that. This is a blank. Or even some characters, if for instance it was here some $sign or percent of which is not sure, that should not be here, it also will put here NaN. All right, so it is very, very handy. And now what we have to do, we have to eliminate all this NaN. And we can do that with this Python code. Just I'll show you that. This is a Python code. Okay, and you eliminate NaN with this one. This only one command, drop NaN. This drop NaN is a command that eliminates all NaN, that includes blanks plus unwanted characters. Okay, so that is what it does. It eliminates all NaNs. So first you just bring all this noise, different I don't know, characters, different things, different signs. Okay, you just convert everything to the pandas data frame, and pandas will do it in terms of NaN, like a blank, and then with this drop now, it eliminates that one. And you have perfectly done the data set. So let us see now. And you have this one. You see all these blanks, all these can be characters, they are gone. Okay. And of course, now you need to do z-scoring because you have different orders in these columns. When you do z-scoring, okay, you will have something what I showed you before. So here will be data in between -3 to +3. So in between this, typically you'll have all your data. So it is standardized. So the same order. Okay, and then the data are ready for processing. So then we did cleaning. Now, in terms of feature engineering, it's also very interesting. I will show you what we do with the data in reality. When we did cleaning, we eliminated outliers, we transform the data into pandas data frame, and then we just did this quite straightforward calculations. So you have a wonderful data set without any blanks, without characters, unwanted. It is clean data. We do strategization, z-scoring. What we do next is the following. So sometimes in public health, we have lots of observations and not many features. Okay. So the proportion between features and number of observations, for example, patients in some community with some disease, for example, right? So usually that the number of features less than the number of observations. Okay, and we call this data toll data, toll data. And I will show you some very efficient algorithms how we can process toll data. Okay. However, sometimes you have also many features here because, as I said, we have data coming not, let's say, from labs, that, for example, from here. We can have data from environment, we can have data, let's say, what was data, how air was clean that day or something like this. And we have environmental data. We have data, it is called SDOH, dog data. It is social determinants of health. For example, age, income, different characteristic for community that is you target and so forth. And this can be very many features here. Environment can also have features and so forth. So then what happens is that you need to know actually that what you have to analyze. Maybe this feature is not so important, and you don't need even to collect data on feature in the future. This feature is very important, okay? And this is selection of which important. We call feature engineering. Feature engineering, feature engineering. And this is the ultimate step in data pre-processing. And in feature engineering, you eliminate features which do not impact much on the results of your processing, of your algorithm. So you can eliminate them because difficulty because you have to do more complicated, more computation. So we need to remove that. It does not affect much your results. And also we do another step before your algorithm. And this step I also will talk next time. And next time we'll start working on realistic public health data, and I will you very efficient methods that we use now. It is advanced methods that we can apply, and you can get wonderful results from public health data. And the most important, you shouldn't worry about how many observations, because sometimes even professionals who get lots of data, they are scared. They say, oh gosh, I have millions of data. I don't know, and I'm frustrated and so forth. So one of the objectives of my classes to alleviate you any fear of working with public health data, even you have millions of observations, is not difficult, and I will show you various efficient technologies that we can use to process data sets, big data sets, and to get a maximum result. You invoke a maximum result from process data set. So we finish for today, and we'll talk about that next time.